Yeah, so good morning. We will start after enough people join. No, there is a lag. Okay. Doesn't matter. Just move it up. Okay. 160.
163. Just now they are joining. Wait.
Huh?
No, they are joining now.
Yeah. I hope you are able to view us and see us. So we are as usual in the college, and we will wait for students to come in and then start. So we'll start in about 5 minutes. Maybe 11:45 we'll start.
Record passing.
Start the webcam also.
Started.
No. Passation.
Okay. So
Start sharing.
So good morning to all of you, and we will start. Okay. So today we are going to talk about graphs. We are going to start talking about graphs, and hopefully we'll get to do a lot of interesting code on graphs. Now this is the third important data structure. As you know, we had looked at linked list or list. We had looked at trees, and now we go to graphs. So today we will do a bit of theory just to get you to understand what graphs are, how do you work with graphs. I think after this we have only one topic left, which is string pattern matching, which will take maybe a couple of sessions, not more than that. So graphs is going to be our last big engagement in this course. So hopefully you will take in this well, and then this is very important because very often commonly used data structure is graph. And what we will do is today, as I said, talk about a bit of theory. Let's see if I can introduce the BFS and DFS for you, and then we'll move on and do one template question on our Flask. Okay, so that's the agenda. So let me start with talking about a PPT. I'll use a PPT to go with graphs. I'll just walk you through the PPT, understand a few things, and we'll move from there. Are you able to hear me? Because I'm not seeing any chat conversation. Are you guys able to hear me? Okay, fine. Okay, good. So fine. So let's start. Okay. So we are going to start with the graph. Okay. Now some basic theory. Some of it will be very boring, but we need to cover it so that we can refer to it later. So a graph basically is a data structure, is a structure used to represent data like this. So we have graph. Generally, when we talk about a graph, we talk about no, we need the.
I will make it.
Just a minute. Generally, when we deal with the graph, we need to know what are vertices and edges. So all these are called vertices, and these are the blue ones are called edges. So graph is a combination of vertices and edges, and an edge UV is a pair of vertices. So we have a edge UV. So if you have to describe this graph, we would say these are the vertices, and then we would describe the edges. AB is an edge. Now this is an undirected graph, because on the edges we don't have any arrows, so it's an undirected graph. And then you have to describe each edge. You describe from the start to the end, or in an undirected graph it really doesn't matter. So you can say AB or BA, doesn't matter. AB, AC, AD, and so on. BE. This is how you describe. These are the set of edges. So each edge is described as a pair. Okay. Each edge is a pair. So this is a very simple graph. Okay. So let's move on. let's rub it. We'll have to rub it after every. Okay. So graphs are used to represent many things. They are used to represent circuits. Not so often, but you can use a circuit because they are connections, and you can represent that as a graph. Very common. They are used to represent roads, links, networks, whatever. So you can see that at the bottom. This is how a graph would be represented, as a set of nodes, which each city has a node. This is, I think, Honolulu, and this is how you would go about defining it. This is LA, Los Angeles, and this is Florida, I think. STL, I don't know. JFK is JFK. STL is Seattle. Sorry.
I think it is Australian.
Washington, huh?
It is Australian graph, sir.
This is Australia.
Yeah.
Oh no, this is America, Baba. Who told you this is Australia?
Seems to be it's Australian
This is America graph, Baba. JFK, all that, America, Northeast. Okay, we'll move on. Okay, so yeah, certain basic terminology. If VO and V1 is an edge, this is an edge, then we say vertex V0 and V1 are adjacent. So these are adjacent vertices. So this is how you represent an edge. The two adjacent vertices which are connected is an edge. So you represent an edge normally as angular bracket V0, V1 is an edge in a directed graph. V0 is adjacent to V1 and V1 is adjacent from V0. That is how you say it, but it doesn't matter. The edge V0 to V1 is incident on V0 and V1. It's an incident edge which is connecting both of them. Okay. Then there is this definition of in degree and out degree. Okay, this definition may be slightly important. The degree of a vertex is the number of edges incident to that graph. So if you have this, the degree of this is 5. Okay. The in degree, if you don't have anything, the in degree and out degree will be same. The in degree of a vertex is the number of edges that have V as a head, and out degree is that which we have V as a tail. So in this case, if I put it like this and I put it this like this, okay, then the in degree of this vertex V, if this is the vertex V, in degree is 2 and the out degree is 3, because 3 edges are going out, 2 edges are coming in, so the in degree is 2, that have V as a head, and these have V as a tail, so that is the out degree. Now there is a small formula which I think you should know. If di is the degree of a vertex I in a graph, n is the number of vertices and e is the edges, the number of edges which is there is e is equal to the total number of edges. Here di is the degree of the graph is equal to sigma di, and so divided by 2. Since adjacent vertices are counted twice, we are dividing it by 2. So the number of edges is equal to this. So because we don't want it to count as 1, you take degree, because degree, in degree and out degree gets counted both, and that is actually 1 edge. So if you add up all the degrees from 0 to n minus 1 and divide by 2, you will get the number of edges. Okay, so this is something you might want to remember. Okay, moving on. Now, yeah, this is some explanation of what is in degree and what is out degree. So if you draw, only here it makes sense. This anyway doesn't make sense because in degree and out degree is all same. For 0, the in degree and out degree is same. For this, it is 3 because 1, 2, and 3. Here also it's 3. Whereas if you look at this graph, there is a little more thing there. For 0, the in degree is 1 and out degree is 1. For 1, the in degree incoming is 1 and outgoing are 2, so out degree is 2. For this 2, in degree is 1 and there is no outgoing edge, so out is 0. So this is how this would come. Okay. So next. some more terminology. The sequence of vertices is called a path, such that the vertices are consecutive. So if I were to describe any path, there could be many paths. So this is a path, and this is also a path. So how would you describe this path? A, B, E, D, C. Okay, or it could be written otherwise also. So this is another path, B, E, D and C. Okay, so this is another path. This is how you call path. Path is a sequence of vertices. It's self-evident. This is some terminology which we should synchronize. Next. Okay, so a simple path is one in which no vertices are repeated. Now this may be important. So no repeated vertices. So this is a simple path. Okay, and this is called a cycle. Cycle are very important to watch because cyclic graphs have their own way of doing, and some of the algorithms will not work with cyclic paths. If there is a cycle in your path, they will not work. So it's important to remember that what is a cycle? That is, some vertex is repeated. Okay, except simple path, except that the last vertex is same as the first, so they are coming back kind of. So this is a cycle. So this is something to watch for in graphs because algorithms are sensitive to it. Next. This is a connected graph and this is a subgraph. So this is connected graph. Any two vertices are connected by some path. This is a connected graph. So this graph is connected. That means from anywhere you can reach anywhere. Whichever way you go, the route may be very long, but you can reach from anywhere to anywhere. That is called a connected graph. Here it's a graph, but it's not a connected graph. This is a disconnected graph or not connected graph because these two vertices cannot be reached from this. Then there is a subgraph, which is a subset of vertices and edges. So you take anything which is this. So just as an example of a subgraph, which is anywhere drawn, this could be a subgraph. Okay, and subgraph is a subset of vertices and edges forming a graph. Maximal connected subgraph is the graph below has three connected components. Okay, so this is a connected component. So each represents a connected component. So there are three connected components. Okay, each is independently connected. So this whole thing is a graph. Okay, and each of them, and this graph has three different connected components. They're part of the same graph, but they are connected within each other and disconnected from the last. So this, each one of them is called a connected component. Okay, each one of them, and though they are disconnected from each other. Okay, and this again is very important because a lot of problems we will need this kind of theory to understand how many connected components do we see in this graph. Okay, in this we see three. Okay, they are individually connected but not connected as a whole. Okay, so going forward, let's see. Okay, now these are different kinds of subgraphs of the graph. So if you see this graph, this is a subgraph of a single vertex. This is also a subgraph where some subset of vertices and edges is there. This is also a subgraph. This is also a subgraph, and similarly for this. Okay, I think you can make that out on your own. Next. Okay, now there is some other definitions which are there, which is called a forest or a tree. So a tree is connected graph without cycles. So this is a connected graph without cycles. So how many connected components? This is one connected component. This is another connected component. This is another connected component. This is another connected component. So connected graph with the this is, they are treating this itself as a graph. Okay, it's a connected graph without cycle. Okay, this is itself, it can be also called a connected component, but they are calling it a connected graph. This is a tree, this is a tree, this is a tree. Now don't confuse them with trees which we saw earlier. This is a tree, and the collection of such trees is called a forest. So there are, in this case, one tree, two tree, three tree, and it depends on how you want to create a forest. The forest could be any number of trees we want to take it. Okay, just think forest is a connected, a tree is a connected graph without cycle. With a cycle, it's a graph, but it's not a tree. Okay, that we know. Then forest is a collection of trees. Okay, some definitions. Okay, now proceed. We move on. Okay, now we have to define what is a complete graph. Okay, if n is the number of vertices and m is the number of edges, a complete graph is one which is very rare, one in which all pairs of vertices are adjacent. So each vertex is connected to every other vertex. If you see here, each vertex is connected to every other vertex. Okay. So how many total edges are there? So each of the n vertices are incident to n minus 1 edges, and however we would have counted each one twice. Therefore intuitively it is n into n minus 1 by 2, and therefore if the graph is not complete, m is less than n into n minus 2, because see, this is the number of edges. You can also get it by doing NC2. NC2. Take any edge and connect it to every other edge. So you have n vertices. So how many edges will a complete graph have? So complete graph will have NC2 edges. NC2 edges for a complete graph. It should have NC2 edges. NCC as in combinatorial C, which comes to n into n minus 1 by 2. This is the complete number. This is the total number of edges. Okay. Edge count. And if m is the actual number of edges, then, and if m is less than n into n minus 1, then the graph is not complete. That means at least every edge is not connected to every other edge. Every vertex is not connected to every other vertex. Then if that happens, then we say it is a incomplete graph. Okay. So in an incomplete graph, the total number of edges m will be will be less than n into n minus 1 by 2. So if n is 5, n into n minus 1 by 2 is 10. So there should be 10 edges for this graph to be a complete graph. If it is less, then it is not a complete graph. Okay. I think it's fairly easy to understand what's a complete graph. Everybody is connected to everyone. That's a complete graph. So total number of edges will be NC2. Okay. So if you look at this, n is 5 and m is 4. M is the number of edges, actual number of edges, 1, 2, 3, 4. So obviously 5 into 4 by 2 is 10 and m is not there. So this is a incomplete graph. If m is less than n minus 1, yes, this is also important. If m is less than n minus 1, then the graph is not connected. Okay, because that means at least one vertex is out of it. Okay, if m is less than n minus 1. Okay, for a tree, m is n minus 1. Yeah, for a tree, m should be equal to n minus 1. That's obvious, isn't it? Because every edge is connected to every edge, at least. This is a minimum value for a tree. Okay. So this is, then if m is less than n minus 1, then the graph is not completely connected, and we can have something like this. That is total number of edges which are actually there, and this is the total number of vertices. Okay. Some equations which you can work out on your own. Okay. So this is what graphs we had seen so far are undirected graphs. So this is an example of a directed graph, okay, where the edges are directed. So they can go only from here to here. You can't go back. If it was undirected, you could go in both directions. Now you can go only in one direction. Fine. So moving forward. Okay. So directed versus undirected graph. An undirected graph is one in which the pair of vertices in the edge is unordered. That is V0, V1. You can go from V0 to V1 or V1 to V0. In a directed graph, one is one in which each edge is a directed pair of vertices. So there is V0, V1 doesn't mean, that means if there is a connection from V0 to V1, doesn't mean there is a connection from V1 to V0. So that is what it means. So if you take this as V0 and this is V1, so V0, V1 means that there is an edge going from V0 to V1 like this, okay, like this. But you can't have, that does not mean that there has to be an edge from V1 to V0, okay. It's not equal to that. In an undirected graph, that was equal. So moving forward, we have to erase that. Okay, moving forward, let's take it forward. Okay. As I said, whole bunch of definitions. Okay, these are the various operations that you do on a graph. Create, insert a vertex, insert an edge, delete a vertex, delete an edge, check whether the graph is empty or not. Then given a graph, this is very important, given a vertex, give all the vertices, list of vertices which are adjacent to that graph. This is important. Okay, rest of it we don't care. Okay, so when you have to convert this into a program, this adjacency is very important. Okay, we'll move on. Now we come to the correct point which we wanted to do. So this is a data structure which you will have to get very comfortable with working with a graph. One is called an adjacency matrix. This is fast, but takes a lot of space. Lot of space. On the other hand, adjacency list is little slow but conservative, but takes less space to store. Okay, so graphs are represented in programming using either adjacency matrix or adjacency list. So we will see in a moment what is an adjacency matrix and what is an adjacency list, and then move on from there. So adjacency matrix is basically if there is a graph of vertices V and edges E, an adjacency matrix is and it's a graph of n vertices. The total number of vertices is n. So adjacency matrix is a square matrix of n into n. Okay, it's an n into n matrix, and if there is an edge from Vi to Vj, that is from vertex I to j, then in the adjacency matrix for that particular ij we have a 1. If there is no such edge, matrix of ij is equal to 0. The adjacency matrix for an undirected graph is symmetric, and the adjacency matrix for a directed graph need not be symmetric, because if edge is there from here to there does not mean there is an edge here. That is for a directed graph. For an undirected graph, Vi and Vj are connected, immediately imply Vj and Vi is also connected. That means we can have a symmetric adjacency matrix. Okay, so I think a good example would be to see an adjacency matrix for a graph. Okay, let's see whether we have it. Okay, yeah, that's what we wanted. So if you look at this graph and see its adjacency matrix, pretty easy to understand. Okay, so this is 0, 1, 2, 3, 0, 1, 2, 3. So you see how it is represented, very easy. Now 0 to 1 there is an edge, so 0 to 1 there is an edge, so we have a 1 here. Okay, this is 1, please. This is row number 1. Okay, let me rub this and write at the bottom. Okay, this is 0, 1, 2, 3. This is the adjacency matrix for this. This is 0. So 0 to 0 we don't consider, there is no loop. So 0 to 0 there is no connection. 0 to 1 to 1 there is no connection. 2 to 2 there is no connection. 3 to 3 there is no connection. Now you see, look at 2. 2 is connected to 3, 2 is connected to 0, and 2 is connected with 1. So this is how it is represented. Now if you notice, 1 is also connected to 0, 2 and 3. So we have 1 is connected to, so vertex 1, which is 1, vertex 1 is connected to 0 here. This is 0, that is not connected to itself, then it's connected to 2, and then it's connected to 3. So that's how you represent. Okay, now I think this is straightforward. Yeah, you can because it's a undirected graph, you see this graph is symmetric around the diagonal. So if you take the diagonal, it is symmetric. Okay, it's an undirected graph, so it's symmetric. Now let's try and represent this graph for a change. This is easy. Let's say look at G4. Okay, so in this case, let's see who are all connected to whom. So this is about how many edges? 8 edges.
8 edges.
So this is 8 vertices. 0, 1, 2, 3, 4, 5, 6, 7. Again 0, 1, 2, 3, 4, 5, 6 and 7. So this is how it is. Now let's understand this portion. These are two connected components of the same graph. This is one graph, please. So therefore one adjacency matrix. Now 0, you see it's connected to 1. Okay, we understand this. 0 is also connected to 2. Okay. Now 0 is not connected to 3 or to anyone else. The only people 0 is connected to is 1 and 2. Okay. Now if you look at, let's say 4 is only connected to 5. So it's not connected to 0, 1, 2, 3, 4, 5. It's connected to only 5. If you see this. Okay. And if you see 5, it's connected to 4 and 6. 5 is connected to 4. This is 4 and to 6. Okay. You see that. So this is an adjacency matrix data structure. Now because it's a undirected graph, it is symmetric around the diagonal because it's undirected. And okay, so this is what is adjacency matrix. Now adjacency matrix is very fast because retrieval is just Aij and you find data directly there. But as you can see, it takes a lot of space. Okay, space consuming, and is represented generally as a two-dimensional array. Right? We in our code we create a 2D array and represent this data as a 2D array. Okay, so that's how adjacency matrix is done. The biggest problem is space, and the biggest advantage is it's super fast because you just go to that value and find out whether there's a link or not. So this is an adjacency matrix. The adjacency matrix becomes a very bad choice of a data structure if, I'll draw it here. Imagine there are 100 vertices. Imagine there are 100 vertices, and on average, each vertex, that is, there is a graph of 100 vertices, and let's say on average, each vertex has only 3 neighbors. So, if you were to represent vertex 0, let's say, it has only 3 neighbors. So, it will have, and it has potentially 100, total number of vertices are 100. Because you have to represent everything, then each row, the row 0, where I am trying to represent 0, it has only 3 neighbors. So some three values in this row will be 1. Remaining values will be 0. So there will be 97 zeros and some 3 will be 1. Which if you see from a storage point of view is catastrophic, because you are just storing zeros and ones. Instead, can't you just store ones or redesign this data structure to show for a given vertex who are all the connected guys rather than storing ones and zeros for everyone. So those are zeros, just forget about them. So for example, 0 is connected to 1 and 2. So can't we use some kind of a list based data structure and just represent 1 and 2? So that is what is the basic argument between using adjacency matrix or adjacency list. On the contrary, if it's a highly connected matrix, that is each not completely connected but highly densely connected, if it's a dense graph, then what will happen? That is one vertex has, let's say on average, about 55 neighbors. The total number of vertices is 100, and every vertex in average has 55 neighbors. So if every vertex has 55 neighbors, then it is better to store it in this way, because there will be 55 ones and 45 zeros. So that's far better than having 3 ones and all other zeros, right? In this kind of case where on average every vertex has 55 and more neighbors, or a good number of neighbors, then we might want to use adjacency matrix. Otherwise, you can, I am sure you will appreciate, if this whole graph has too many zeros, it's not good to use that kind of space and waste it, okay, on any system. So I think you should keep that in mind as we go to the next slide. Okay. So, okay, some merits of the adjacency matrix. Let's talk about the merits and then we'll see the alternate data structure, which is called the adjacency list. Okay, so from the adjacency matrix, to determine the connection of vertices is easy. Okay, so the degree of a vertex, if you want, it's pretty easy to do that. You go through one row. For example, if you're looking at a vertex I, if you go to the vertex I, that means you look at one row I and count and go through all the j's from j equal to 0 to n minus 1. You go through the whole row, you will know what is the degree of a vertex, because these are the people who are connected to it. You can just do sigma on that and you can find out the degree of the vertex. Wherever there are that many ones, count number of ones, that will tell us. For a directed graph, the row sum is the out degree, while the column sum is the in degree. Now this is important to understand. For a directed graph, the row sum is the out degree, because if you see, how do I represent a row? Okay, let me just take a, okay, let's try and draw here. If I have a row, if I have a vertex, if vertex V1 is connected to vertex V2 or to any other vertex, all those will be 1. So this row will represent the out degree. The number of ones here will represent the out degree. That means it's going from 1 to all these people. That is used to represent the out degree. On the other hand, if you have a column, that column will represent the in degree. Okay, that means so many are coming here. For so many, he is the in degree, where the column sum is the in degree. Okay. Now, if you go back, can we go back? Yeah. So if you see this, I mean, here of course it's not a directed graph, but if you will see, just understand this column. If you understand any column for that matter, okay, what does it mean? If there are a number of ones, that means from this guy something is coming to him for this vertex. From this guy something is coming to him. So if you count the number of ones in the column for a particular vertex, this is a row for a vertex, this is a column for a vertex, you will get the in degree. So the sum of rows, sum of ones in a particular column will give you the in degree. Sum of ones in a particular row will give the out degree. Okay, so that's important, because wherever there is one, that means there is a graph, there is an edge from here to here. That is from 0 to 1 there is an edge, from 0 to 1, from 0 to 1 there is an edge, 0 to 2 there is an edge, which is what we are representing here. So in this case, of course, the in degree and out degree will be same, but in a directed graph this can vary and will vary generally. Okay, so we move on. Okay, let's okay, so how do you represent an adjacency list? Now adjacency graph we have seen, which is just a adjacency matrix we have seen, which is just a two-dimensional data structure like a matrix. Now there is a data structure which is pretty popular, is called adjacency list. Okay, so how do you do the adjacency list? So what you do is you have a data structure in which for every vertex, where you store the ID of the vertex, then you have a linked list of all those vertices which are connected to this vertex only. So this linked list, as you can see, it is starting a linked list. So this linked list will contain only those vertices which are directly connected to this vertex, so that they represent the edges. So it will not store all the, suppose it's a 50 by 50 matrix, because your number of vertices are 50. In a matrix, you'll have to create a 50 by 50 matrix. Here, what will you do? You'll have 50 vertices, but for each vertex, you will store only those guys who are directly connected to each. So for example, for vertex 0, if vertex 1 and vertex 2 are only directly connected, no one else, then we'll keep it that way. Okay. And let's say vertex 4, if there is a vertex 4, it is connected to 1, it is connected to 3, and let's say it's connected to 7. Okay, we'll record all of that. So this will be a linked list only to record who is connected to 4. And here who is connected to 0, only they will be sitting in the linked list. So you don't have to create a gigantic matrix of 50 by 50. You have to create a single array, and each of the elements of the array will be a data structure, which will be a pointer to a linked list, which will indicate that this vertex is connected to which other vertices. Okay, so that's how it is. So something like this will be there, and the graph will be a collection of this kind of vertices, where each one of them is a node pointer. Right? Okay. Node is this. Okay, let's see whether we have a picture like that. Yeah. So this is the alternate way of representing this. So let us again look at this, because here everybody is connected. So here is a it's a bidirectional graph or undirected graph, which means 0 is connected to 2 and 2 is also connected to 0. But just see how we keep it. So 0, we allocate a node 0. Inside node 0, we have a pointer. We don't have a complete 2 by 2 array or a 7 by 7 array. In every element we store a pointer, the head pointer of a list of what? List of vertices which are connected to it. It's like a linked list. So this is an adjacency list. So you have a head node and you have all the vertices which are connected to it. Okay, directly, like this. So this is very conservative, or it saves a lot of space while storing it. Very, very good from a space perspective. Okay. So we'll move on. So we've talked about adjacency list and adjacency graph, adjacency matrix. These are the two common data structures. Now some of the operations that you do on a graph are, you ask what is the degree of a vertex. We know how to do that. Degree, we can get in degree and out degree. For a undirected graph, both are same. For a directed graph, we talked about out degree is the sum of the rows, sum of the ones in the row. In degree is the sum of the ones in the column. Okay, so that is called in degree. Number of edges in a graph we can always get is determined by the number of vertices, n plus e. We know how to get out degree, we know how to get a in degree. Okay. Yeah, in this case in degree becomes difficult. No, go next. So the graph traversal algorithms, just like in a tree, we talked about 3 or 4 traversals. We talked about pre-order, in-order, post-order. Then we talked of a level order traversal. I don't know whether we did a level order.
We did.
We did in the class.
Yes.
Okay, we did a level order traversal. Here there are basically 2 kinds of traversal. These are very common and you should know them very intimately. One is called depth first search and the other is called breadth first search. So you should know both of them reasonably well. Okay, so we will have to write code and you have to get adept. One of the objectives of this semester is that you should be given a graph, you should be able to write a DFS very easily or a BFS very easily. So that's one of the objectives. So if not today, I think in a later class we should be able to write DFS. So please make it a point that you will not go out of this course without being able to write a DFS and a BFS clearly. Okay. Okay. So let's talk about what is DFS and what is BFS. So I think we have given a graph and we are doing a depth first search starting at F. Okay. Now, from the adjacency list, if you are using an adjacency list, we can determine who are the neighbors of F. Okay. In this case, it appears, I don't know what this means, but it appears that the neighbors of F are A, E, and I. Okay. The neighbors of F are, from F you can go where? You can go to A, E, and I. So that is how it will be represented. So from F you can choose any of its neighbor to go, and then you can go depth first. Okay, I think there will be a better picture than this to illustrate depth first. A depth first search in an undirected graph is like wandering in a labyrinth with a string and a can of red paint without getting lost. I think that is a standard way of talking about it, but it's easy to see with an example. So we start at a vertex X and tie the end of our string to the point, painting S visited. Next we label. Okay, I think it's better to see this through a bit of algorithm work, a bit of PPTs if we have them. Let's see if we have them, to understand how DFS works. Okay. Yeah, let's see. Yeah, let's see if we can pull a PPT to show you how DFS works. It's pretty simple. Okay, so let's write the graph traversal. Now we may have some animation also.
Yes, sir. Online.
Let's do that. No? So let's do some animation of depth first.
Online.
Okay. So we have the graph given. So it's a directed graph. It's a small graph. If you want undirected, we can do undirected also. Now, no, let's go for directed. So we are going to start. We can choose any start vertex 1. Okay, and can't enter. 1. No, don't run yet. We have to be able to run it slowly.
One.
Yeah, 1. No, now if we start from 1, okay, watch this before you see the animation. 1. Who are the neighbors of 1? It's 2 and 3. Sorry, 2 and 3. These are the neighbors. So you can decide to go to either 2 or 3. Okay. So once you go, let's say to 2, you can't travel further. So then what you do? Then you go to the other neighbor. Okay. Otherwise, chase the neighbor to its depth. So now, if you are starting at 1, okay, if you are starting at 1, first if you can go to either 2 or to 3. Any one is valid. So if you go to 2, then you get stuck and you can't do anything there. Because you can't proceed, this 2 is over. Then you say 3. Now 3 you go. Now 3 has what neighbors? 3 has 5. That's the only neighbor 3 has. So you can do 1, 2. Then you are back. Okay. Then you do 3. Okay. Because you can't do anything more with that. At 3 you have only one neighbor. So the only thing you can do is go to 5. 5 perhaps you have a choice. How many neighbors you can go from 5? 3. 3 is already visited, so you shouldn't go there. Things which are visited already, you shouldn't go there. So one is 5. Sorry, you are at 5. You can't go back to 3 because this is marked as visited. 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 And 5 is also marked as visited. So from 5, you can't go back to 3. Because that is already visited. Can you go back to 1? No, you don't want to go back to 1 because that's also visited. So the only option left for 5, though these are neighbors which he can go to, The only option left for 5 is to go to 6. Okay, so he will go to 6 because there is no other option. So now he is at 6. Okay, now remember 5 had other, no, there was no other neighbor for 5. So the only other neighbor for 5 was 6, it went to 6. Now for 6, if you watch, there is only one neighbor which it can go to, which is 7. So it will mark 7 also as visited.
6 also are visited.
So that's it. So 7 is visited. So from 1, this is, if it had gone to 2, then 3. Now it can, so from 1, if you see, it could have gone to 2, it could have gone to 0, or it went to 3. It could have gone to 3. If it went to 3, this is what would happen. Now 1 to 2 has been exploited already. 1 to, and then 3 has also been exploited because you can't go more than 2. Okay, you get stuck there. And then comes 3, because that's the other thing which is unexploited here, we saw here. And once 3 is explored, then we have 0. So this is one possible way you can do this. There is no hard fast rule that this should come out, because it depends. You may want to chase 0 first, then chase 2, and all of that. Now if you're starting at 1, you will never go to 4, because there is no way you can go to 4 at all. So let's see what the animation shows you. So the depth first. Okay, let's see the adjacency list representation. Now this is good. First let's reduce that and show the adjacency list for this graph. Okay, this is how the adjacency list would look. Now the problem is you are not able to see the graph, but what this represents is 1 is connected to 0. Okay, I don't know what the second value they are using it to represent. 1 is connected to 0, 2 and 3. Okay, I don't know what the second value represents. These are the vertices, and this is the pointer, I think. I don't know.
From 1 it's saying.
Huh? No, 1 is connected to 0. Again, go back to the graph. What all 1 is connected to? Yeah, 1 is connected to 0, 2 and 3.
Yes, sir.
So go to the adjacency list representation. 1, 2 and 3. No, that is okay. What does this? Sorry, 1 is connected to 0. 1 is connected to 0, 2 and 3. No.
Yes, sir.
Now what does this 1 represent?
Again from 1 is
Okay, let it be. Then 2 is not connected with anyone. Okay, 2 doesn't have an outgoing edge to anyone. Okay, these are all outgoing edges from 2. Okay. 3 has an outgoing edge to 5. That's it. 4 has an outgoing edge to 2. Then 5 has an outgoing edge to 1, 3 and 6. This is important. 5 has an outgoing edge to 1, 3 and 6. Can we just check that? 5.
Just is marking as visited as 1, sir.
Acha. 5 is 1. 5 can go to 1, 3 and 6. So that is what it is. See this. 5 can go to 1, 3 and 6. So that's how the adjacency list of the graph looks. Okay. 6 can go only to 7 and 7 can go to 5 and 6. That is how it is. This is the adjacency list. Now it's good. You can see the adjacency matrix of this. Now this is how the adjacency matrix. Okay. This is how the adjacency matrix looks. Now you can see that the adjacency matrix, when it is 7 by 7 itself, has so much of white space. So all that is zeros where there are no connections. So it's a wastage. So that's why people don't prefer this data structure. They like the adjacency list more. Okay. So now let's run a DFS very slowly and see how it runs. We have to keep also a visited array because we don't want to revisit everyone. Initially, you see the visited array is all false, okay? Because we have not visited any vertex yet. So we'll start and watch the DFS unfolding. So we go back to the logical representation.
Click on run.
Or you can even look at the adjacency matrix representation. And we'll start the thing from 1. So if you see from 1, the neighbors of 1 are 0. So it goes to 0. Now 0, there is nothing to do because 0 just gets displayed. So yeah, you can do it on your own. So it's going to each vertex from 1, that is 3, 5. Okay, I think you can do it on your own. Now see what is happening here on your left. Okay, wait.
Stop. Animation slow.
Achha, this will, watch this. From DFS, it has gone to DFS 0, DFS 2, DFS 3. Then it will come back and restart what has been left. Okay, because it's depth first. Okay, I think more than this, maybe a PPT will help. This you can do on your own and check. Okay. No, this will be difficult, no?
Yes, sir.
PPT on that.
Hacker Earth is more clear.
Hacker Earth?
Visualization.
Better, huh?
No.
Okay. So let's look at Hacker Earth visualization of a DFS. Okay. This is better. This is better. Okay, so yeah, let's follow this through. So we have A and all the directed edges are there. So we start from A, I guess. And when we start from A, who are the neighbors of A? The neighbors of A are C, because there is a bidirected graph there. And the neighbors of A are also E. So we have to pick one of the neighbors and chase that neighbor. So we add A to the stack, okay? Then we process AC. So it's going to C and not going to E. So AC. Then he is on C now.
Yes, sir.
So he is on C. Okay. Now let's go to C. Okay. Mark node C. So C is marked as visited. Okay. So from A he found out who are the neighbors from the adjacency graph or adjacency list. The neighbors are are C and E, neighbors of A. Now he can go to either one. He decides to go to C. Now when he decides to go to C, what happens is he says A is already visited. Because he is going to C, C is also marked as visited. Now what he has to do? So now he has to go deeper with C. So when he is going deeper with C, he finds out who are C's neighbors. He discovers C's neighbors are only B and F.
E and F also.
E also.
F also.
So C's neighbors are E, F and B. These are C's neighbors. So he has to pick one of them arbitrarily. All are eligible neighbors. He has to pick one of them. So let's see who he picks. So he picks CB. Okay. So you have CB. Now, okay. Now see the stack developing. First you are on A. There is some unfinished business of A also, because A had another neighbor E which we are yet to process, but because it's depth first, we are going deeper with C. Now we are chasing C. C has three neighbors as we talked about, B, E and F. It decided to go with B. It can go with anyone. So it pushed B also onto the stack. So right now on the stack are B and C and A, because B also has unfinished business. So now he goes to B. Now does B have a neighbor? Yes, B does have a neighbor which is not visited. the only neighbor B has, B has which is not visited, it can't go to C. Though C is also B's neighbor, it can't go to C. It has to go to F. Okay, so it goes to F. C is already marked, so it goes to F. So it adds F to the stack. It will soon add F to the stack. Mark node F. F is marked as visited, and yeah. Now we chase the root from F. So now what happens with F? F has how many neighbors? F has C as one neighbor, B as another neighbor, and E as another neighbor, and D as another neighbor. So it has C, B, D, E. These are all the neighbors of F, out of which it can't go back to B. So it has to try either D or E, which are the unvisited neighbors of F. So let's see what he tries. Okay, so he's going to D. Okay, so he's going to D. So now F has gone to D. Now D, does it have a neighbor? Yes, it has a neighbor C, but it's already visited, so there's nothing to do with D. So now D is done. You can't go anywhere from D. All its neighbors in D are gone. So now D can be popped from the stack because there is nothing more to visit in D. So D gets popped. Okay. C is already visited. F is already visited. These are the neighbors. Okay. Because none of the neighbors of D are yet to be visited, we can get rid of D now. So you see D is popped off the stack. Now who is there on the stack? Where we went to D was from F. So it's now backtracking kind of. So it went to F. So F had D as one neighbor, and it also has C. C of course was already visited, so we didn't look at C. B was also visited, we didn't look at B. So D we went, and now F has an unvisited neighbor called E. So we'll now go to E. So E gets added to the stack. Okay. Now if you look at E, E has how many neighbors? A has one neighbor, and that's it. That's the only neighbor E has. F is also a neighbor.
Yes.
Yeah, F is also a neighbor of E. Now both the neighbors A and F are already visited, so E can be taken off the stack. Node A, so pop E off the stack. Now we return to F. Now you see F has some neighbors, D which is already visited, C which is already visited, B which is already visited, E which is already visited, so we can pop off F also. There is no unvisited neighbor of F. Now you will see there is no unvisited neighbor of B. There is no unvisited neighbor of C because all are visited now. Yeah. So we pop all of them. Now, question is, we did a traversal, which is DFS. Now, as we traverse a node, we can display it. Okay. Here we have not done that, but we can do that. Okay. So that's how we complete depth first search. I really recommend you should go through depth first search, look at it for a moment, and then come back. So before we go to breadth first search, I will take a pause here. We will code depth first search. We will write our own program for depth first search and then proceed to breadth first search. So in the next session on C++, data structure C++, let's write a depth first search and proceed. Okay. So does this make some sense? No. Okay. At least some of you are alive. Okay. Okay. Now we have looked at depth first search. You can see for yourself also how depth first search works. Where can we get the PPT?
Dashboard.
Okay, we'll put it in the dashboard.
Study material.
In the study material, we'll add this PPT. There are many PPTs like this. It's nothing great. I think the Hacker Earth is better. Hacker Earth or Hacker Rank?
Hacker Earth.
Earth. Okay, Hacker Earth, look at it. So that's far better. And you can understand DFS better. In the next session, let's write code. And then we'll move on to BFS. Then we'll write code for BFS. I think next session we can do BFS and code for BFS also. Okay, let's see. If you are able to do that, then we will have some more in graphs. What all is there in graphs? Okay, whatever. There will be some minor areas to go through in graphs. Okay, so we will stop here as far as data structure is concerned, and I just want to show you how to do a template in Flask.
Spanning tree we have.
Spanning tree. Okay, minimum spanning tree. Oh, that is okay. Both are there, Kruskal's and
No,
Print.
sir. Only
Only
spanning,
graph.
only spanning tree of graph. That is
Okay, only spanning tree of graph. Okay, fine. So we will do that. Okay, how to discover a minimum spanning tree or a spanning tree? Fine. So we will do that in the next session. Now in this session, we will illustrate how to work with graphs. With templates of Flask. Okay. So we are switching. So I'll pause for about a couple of minutes here. What time we have time till?
130.
1:30. Oh, okay. So we not need till 1:30. Yeah. So okay.